Ayla Gafni, who graciously agreed to speak on short notice, and she's going to be telling us about asymptotics of restricted partition functions.
All right, thank you. Thank you for the invitation to speak here. It's always exciting for me when I get to come back to Vanderbilt because I did my undergrad and my master's here, so I feel like I'm at home. Yeah, so I'm going to be talking not about mock theta functions, but more about sort of circle method ideas, the partition theory from a different perspective and using maybe different language to kind of study the same problems. But it is the same topic. So we have the same title, first slide that everyone else had, which is that a partition is a way of writing a number as a non-increasing sum of other numbers. And so we have our classic example that everyone loves, which is that there are 5 partitions of 4. And if, so in case we forgot or over lunch forgot what a partition was, we're going to be looking at partitions. And the study of the asymptotics of partitions started with Ramanujan in 1918, or it didn't start in 1918, but that was when Hardy and Ramanujan found the asymptotic formula for the partitions, which is usually not written necessarily in this format. I've written it in this way as a constant times an exponential of a power of n times, or I guess divided by another power of n, because over the course of this talk, we're going to be looking at a pattern of various partition functions. And if we write it in this way, it's a little bit easier to see what that pattern is. So, so this is general integer partitions, classical partitions. And what I'm interested in is restricted partitions. So we're going to take a subset of the integers, pick your favorite subset. And the only restriction I'm going to put on it is that the GCD of that subset of the integers should be 1. And then we're going to let PA of n be the number of partitions of n where all of the parts are coming from that set A. Okay, so you could pick the primes, you could pick the odds, you could pick the square numbers. And the reason we have the GCD restriction being that the GCD is 1 is that if we have a common divisor, then silly things happen. Like it's very hard to partition 7 into even numbers. And so that's not helpful. If we have only even numbers, then we can't partition every number. And also if we have only even numbers, we could divide out by that, whatever that common divisor is, we could divide out by it, and then we don't have any new information, right? We just get back to the original case. So we're going to look at relatively prime sets. And so the question is, for which sets A can we count PA of n? So what do I need to know about the set A in order to get an asymptotic relationship, an asymptotic formula for this restricted partition function? And we're going to explore that a little bit more. But let me preface this by saying that I am not the first person to think about this question. And the results that I'm going to state are all things that happened in the last 10 to 15 years. And they are not the first results in this area. This idea of looking at restricted partition functions has been studied immensely and extensively by these people on the screen, Bright, Bateman and Erdős, Broken, Roth, Sakaris, and Caruella, among others. This is not an exhaustive list. There are various results for very general A. They tend to use complicated formulas and long and difficult proof methods. And so what I'm focusing on is one specific way to look at this and see as a pattern in certain circumstances. And so I'm going to call these modern examples of restricted partition functions. Okay, so the first modern example that I'm going to talk about is partitions into kth powers. So in case, just to make sure that everyone's on the same page about what I mean by a restricted partition, we have an example. So we're going to look at kth powers. So fix a power k, and I want to, my set a k is going to be all of the perfect kth powers of the integers. So for example, there are 4 ways to partition 10 into squares. You could do 9 plus 1, 4 plus 1 plus 1, 4, and then a series of ones, or just all ones, because those are the only 3 squares that are less than 10. And so I looked at this as part of my dissertation research. So in 2016, again, I was not the first to prove this result, but I did it in a different way using what I'm going to talk about in a minute. So the number of partitions into perfect kth powers is given by this asymptotic, and the constants they're given explicitly in the actual paper, and all of the results are going to sort of have this form, and all of the constants are going to be suppressed for the sake of clarity and for the sake of fitting the result on one slide. We're not going to write out exactly what C1 and C2 are. They're similar to those big constants that you saw in Michael's talk, right? So this big constant and then exponential. So we have a constant depending only on k, an exponential of another constant times n to the 1 over k plus 1, and then divided by this power of n. And so, and the case k equals 2 was due to my advisor, Bob Vaughn, and then I generalized that to kth powers. And then from there, we can go further. So instead of just kth powers, we can look at powers in a residue class. So we have AK sub AB. This is the notation that Bernd, Malik, and Zaharescu used. We're going to look at kth powers where the x, the number that you're taking a kth power of, is fixed to be in a specific residue class. And Bernd, Malik, and Zaharescu in 2018 found that the number of partitions into kth powers in a residue class is given by, again, this constant, an exponential times a constant times a power of n, and then divided by another power of n. And we see that that this exponent is getting a little bit more complicated, and that's because the set that we're working with is a little bit more complicated. But in general, it is a generalization. If we were to look at the partitions into kth powers themselves, that can be gotten by looking at a equals 1 and b equals 1, or a equals 0 and b equals 1. I don't remember which one they're looking at there. But one of those, and then it's probably 1 and 1 because you need to be relatively prime, but doesn't matter. And then if you look at k equals 1 in either this or the my 2016 result, then you get back to Ramanujan's result exactly. And this can be taken one step further because kth powers and kth powers in residue class are both values of a certain polynomial. And so in 2018, it also Dunn and Robles generalized this further to any suitable polynomial. And by suitable, I just mean that the GCD of the values of the polynomial should be 1. It's really all you need. And then that it should take integer values to integer values. So it doesn't actually have to be an integer polynomial. And you get, again, the same sort of format. So for all of these results, I've changed the format. This is not exactly how they're written in the papers because they write it in terms of the actual constants, and these C1 and C2 constants are slightly varied from one result to the next, but I've done it this way so that we can see that they all sort of take the same form in the end. And it's the Zoom thing is covering up what that says, but this zeta of 0 alpha is an appropriate Matsumoto-Wang zeta function, which is, I'll explain what that is in a minute. It just,
you can just spit out some of the roots from memory.
Yeah.
Yeah, that paper's not written that greatly, to be honest, as a graduate student, but yeah.
I mean, all of these 3 results were papers written by graduate students.
Yeah,
so
it was hard.
Okay, so now we've done polynomials, and so okay, you might say, but I didn't pick a polynomial set as my favorite set. I picked the primes. So what can we do with the primes? So in 2007, Vaughn looked at partitions into prime numbers, And you see that it does still take this same format. It's a little bit more complicated because now instead of n to the, so whereas Ramanujan's, Hardy and Ramanujan had n to the 1/2, we have pi of n to the 1/2 because that's, we're now looking just at the prime. So this is how fast the primes grow. And then we also have an extra log n, and that's again because of the prime number theorem that's hidden in this result. And so actually in 2020, around the time that this conference was originally supposed to happen, I was looking at how partitions into powers of primes. So combining the kth power stuff from the previous slides with Vaughn's work in partitions into primes to see if we can get an asymptotic for powers of primes. And so we do have this same sort of formula that we have a constant and then an exponential times a constant of the growth function to k over k plus 1, and then we have divided by some powers of n log n. And so we have now 5 modern examples, right? Of course, there are other examples of restricted partition functions, but these 5 results were all proved using similar methods. And in fact, the proofs in some ways are parallel throughout. So there's certain places where you could just go along and then it's like, okay, now I need to insert here certain information about the set A, and then, okay, now continue the same way. And so for the rest of this talk, I'm actually going to give a sketch of the proof of how all 5 of these results would work and what's different. What do you need to know about A? Where do you need that information to come in? And what's similar and what's different as you go through these. Okay, so all of these were proved using the Hardy-Littlewood circle method, and we need to start with a generating function. So the partition function, the original partition function, has this generating function, which is this infinite product of 1 over 1 minus z to the m. And if you haven't seen this before, it's actually not that hard to see why this is the generating function. So if you take that right-hand side and you write 1 over 1 minus z to the m as a geometric series, and you expand out each of these geometric series, then we have a partition. If you want to construct a partition, well, one way, and you don't care what number it is a partition of, one way to do that is you choose how many 1s you want, and that would be choosing a factor from here. You choose how many 2s you want, you choose how many 3s you want, and so on. And then when you're done, it's going to add up to something, and it's going to be a partition, and it's going to count as a coefficient of z to the n. And so it all just sort of shakes out and takes care of itself, and you get this as the generating function. And when you construct the generating function in this way, you can get automatically a generating function for any restricted partition function, because if I'm only, say, taking the primes, well, then I wouldn't allow 1 as a part, and I wouldn't allow 4 as a part, so I just cut those out. And so restricting to the set A, the generating function is, again, this product of 1 over 1 minus z to the a, where now I'm only taking A in my set. Okay, so now that we have our generating function, we're going to put that into the Hardy-Littlewood circle method. And so, so the circle method, we're going to use Cauchy's theorem for this. So Cauchy's theorem looks like this. It says that the nth coefficient of a Taylor series is given by this, this particular integral, and this is normalized. So this is written from 0 to 1 instead of 0 to 2 pi. And so it's normalized that way. We have E of alpha is e to the 2 pi I alpha. And I've written this in polar coordinates. So we've got rho is our radius and alpha is our angle. So that we're integrating around a circle here. And so what we're going to do is we're going to take our radius to go to 1 and as close to 1 as we can. We can't go exactly to 1 because it wouldn't converge anymore, but we can go really close. And the way we're going to get rho to be very close to 1 is we're going to write rho to be e to the negative 1 over x for x, some very large number. So X is the parameter that we're actually going to be working with, and that's going to tell us how close is our circle going to be to 1. Okay. Now the generating function is given as an infinite product, and it's much easier to work with an infinite sum than an infinite product. And so we're going to take the logarithm and in fact work with this different phi of a of z is what we're going to put exponential phi of a. Okay, we're going to put exponential phi of a of z into here instead of psi, so that we can work with sums instead of products. Okay, so here's the philosophy behind the circle method. If alpha, so we're left with this integral, right? This is the goal. We need to figure out what this integral is. And we're integrating with respect to alpha. And the way the game works is if alpha is close to a rational number with small denominator, then we have good estimates for the integrand. And more than that, the major contribution, the main term contribution comes from those points that are close to rational numbers with small denominator. Everything being in quotes, because what does it mean to be close? What does it mean to be small? We get to decide that to some extent. Okay, so those regions that are close to rational numbers are called the major arcs, and they contribute the main term. And the gaps between major arcs are called minor arcs, and they're absorbed into the error term. So that is the traditional philosophy behind pretty much any Hardy-Littlewood circle method problem. Okay. What's different in the case of these 5 results about restricted partitions is that actually the only main term comes from the principal major arc at the origin. So this alpha close to 0 is the only main term contribution. And so we're actually going to split up into the principal major arc, the other major arcs that are close to rational numbers that are not 0, and then the minor arcs are the rest, right? And you could say, okay, well, why don't you just call all of this minor arcs? And why are we splitting it up this way? Like, why not just put this into the minor arcs? And you can do that. It's called the saddle point method, and Tannenbaum does that. And he gets slightly, I mean, the same results, but he gets it works in slightly different contexts. There's sometimes when that works better, and sometimes when the way I'm going to do it works better, and it just depends. But the reason I'm not just calling these minor arcs is because I'm going to treat them like major arcs. So the techniques that we use to study the major arcs are different than the techniques that we use to study the minor arcs. And so these I'm treating like major arcs, and then I'm going to say, okay, they're small, put them into the error term. So that's the game plan. And we're going to go through each of these regimes, the principal major arc, the major arc, the other major arcs, and the minor arcs to see how this works. Okay, so let's look at the principal major arc first. So this is going to be our true main term. And so then we're looking at alpha close to 0. So in our integral, which I'm sure everybody remembers exactly what that integral looks like. In our integral, we had phi of rho, we had the exponential of phi of rho of e to the alpha. And so if alpha is 0 or close to 0, then we basically just have phi of rho. And so phi of rho is given by this, where again, remember, rho is e to the negative 1 over x. So that's why I don't have a rho over here, I have an x. So we end up with this sum, e to the negative ja over x divided by j. And we are going to use a Mellin transform to turn that into an integral. So I've taken this exponential here, and it's become this integral using the magic of Mellin transforms. And then we're going to bring the sum over a inside. Okay, so then the only place where we have a's in here is we have this sum over a and then an a to the negative s here. And so in order to understand how this integral works, I need to understand how this sum of a to the negative s behaves. And eventually I want to put this into a residue integral. So I need to know the zeros, the poles, and the residues, and anything else you would need to do residue calculus on this sum. Okay, so how does that work in the specific cases that we have with these different sets A? So if we have kth powers, then we have a to the negative s is basically n to the negative, it's exactly n to the negative ks. And that gives you zeta of ks. And this function has been studied by a few people. So we know some things about it. And we, in particular, know, we do not know all the zeros, but we know all the zeros in the range that I'm going to be looking at. And we know the poles and the residues and all that. For kth powers in a residue class, it's similar. You get a Hurwitz zeta function. It's just a slightly different denominator, but this has also been studied. And so you can go to the literature and you can find all the information that you need. For polynomial values, you get this Matsumoto-Wang zeta function, which again is also studied, and we can look this up and it's fine. For primes and prime powers, you get a prime zeta function, which has been studied but is more complicated than the other zeta functions that I've mentioned, because the prime zeta function behaves basically, I'm going to not touch the mouse. The prime zeta function behaves basically like log of zeta. And so you end up with extra singularities at all the zeros of zeta that are going to give you problems. So you have to be a little bit more careful when working with the prime zeta function. Okay, so how does this factor into what we're looking for? So this is what we had on the previous slide, except that I've brought these sums inside. So we had this outside, we had a sum over A that I've brought inside, and that's in the big parentheses. And then we had a sum over J that I've also brought inside, and that's what's creating that zeta of S plus 1. That's the sum over J was basically just J to the negative S plus 1. And so this is what we're looking at, and we want to evaluate this using a residue contour integral. And so zeta of S plus 1 is going to be fine. Gamma of S is going to be fine. We need to worry about this Dirichlet series. So for powers and polynomials, the special zeta function, it has a meromorphic continuation. Everything is fine. We're going to have a double pole at S equals 0 coming from zeta of S plus 1 times gamma of S. And we're maybe going to have a simple pole. I didn't mention it on the slide, but we're maybe going to have a simple pole at S equals 1 over K or something that's coming from the zeta of KS. We also have to deal with that, but that's all manageable. For primes and prime powers, we have to analyze something that looks like this. The prime zeta function behaves like log zeta. And so we end up with a log zeta of KS. And then we have these logarithmic singularities at every zero of zeta. So you can't just take a contour around it. We have to stay in a zero-free region of zeta. And so we can use a keyhole contour to sort of carve out what's happening at S equals 1 over K and then make it work that way. So it's still manageable, but you have to be a little bit more delicate because you have these logarithmic singularities happening. Okay, so that's the principal major arc. So now let's see what happens on the non-principal major arcs. So now we're looking at alpha being close to a rational number with small denominators. So the alpha here is going to be R over Q plus beta. So beta is small, Q is relatively small. And so this right-hand side is what we need to handle. And what we're going to do is we're going to split it up in terms of residue classes. And then that way we can isolate what's happening depending on the set A, and then the pieces that don't depend on the set A. And so what we really need to understand is how A behaves in residue classes, because if I know how many terms there are in this sum, then that can help me bound that exponential sum. And then once I have a good control over this, then I'm just left to evaluate this sum, and this sum doesn't depend on the set A and has been well studied. There's whole chapters about it in Bond's book on the Hardy-Littlewood method, so we'll be fine. Okay, so we need to understand how A is distributed among residue classes. Okay, so for kth powers or polynomial values, we can do this. It's fine. It's just solving polynomials mod Q. We know how many solutions there are. We can take our denominators up as high as we want, up to the power of X, and we end up needing to analyze this exponential sum, which is standard. For primes and prime powers, we have, is a little bit more delicate because we have to use Siegel-Ballfisch theorem, which is only valid up to a power of log x. And so we can't take our major arcs by when we choose how small we want our denominator to be, we can't make our denominators as large in the primes and prime power cases because we're limited by Siegel-Wallfisch theorem. And then we end up needing to analyze this exponential sum, which it turns out that there's a nice relationship between these two exponential sums, and we can get exactly what we need. So the goal in all of these cases for the non-principal major arcs is to bound this sum, this SQ of A. We want to bound whatever we get by some constant 1 minus delta factor that does not depend on Q, right? And so the trivial bound is going to tell us that there's Q, that this is less than Q. We want some uniform bound on this. And so the reason is, so this is the result for partitions into prime powers written again. So the main term of partitions into prime powers was given by this form, right? And so in the exponential here, we have a constant times 1 times pi of n to a power, right? And so if we can save in the non-principal major arcs, if we can save a constant factor, then the non-principal major arcs will look something like this. And here I have this 1 minus delta, which means that it is exponentially smaller than the main term, right? So as long as I can just save a little bit that doesn't depend on Q, as long as I can save just a little bit, then I've won over the main term. And now it doesn't make sense to even figure out exactly what it is because it's all error term. Okay, so that's the non-principal major arcs. And in all the cases, you can get this 1 minus delta, and the only main term contribution comes from the major arc at the origin. Okay, and so then we've dealt with all the major arcs, we're left with the minor arcs. And the minor arcs are for generic alpha. So we don't have any information now because it's just whatever's left over. So we don't have any information about alpha anymore. So this is just the definition of phi rho E of alpha. And so I'm going to take this one here, this e to the negative a j over x, and I'm going to write it as the integral from a to infinity of e to the negative jx over x. And so then I have this, then I bring the sum over a inside. So then I have this integral to deal with. And now the only piece that has anything about the set A in it is right here inside in the innermost part of the integral, right? So I've isolated that by itself. And so now I need a good estimate just for this vile sum for any integer j, and where a is the element of my set. All right, so I need to understand how this vile sum works. So we have these special exponential sums. And for kth powers and polynomial values, this is the exact exponential sums that come up in Waring's problem in all of the traditional circle method problems. So this is really well studied, Weil's inequality and Pois's lemma. Like the traditional minor arc treatment gives you exactly what you want. For primes, you can also use classical techniques that came out of the Ternary-Goldbach conjecture, because now we're looking, that was also looking at sums of primes. For prime powers, we have some Waring-Goldbach results. They're less developed, but they exist. So there are decent upper bounds for these vile sums over when you're taking a sum over powers of primes. But you need to be careful about ranges and conditions on alpha. And so here we need to be delicate and make sure it works, because the remember the Siegel-Wallfisch theorem says, oh, we can't take Q very large, right? So we need our minor arcs in some ways to be bigger, right? Because our major arcs are limited. But now the Waring-Goldbach conjecture, or not Waring-Goldbach conjecture, but the Waring-Goldbach results on these vile sums are also restricting how big our minor arcs can be. And so we have to, there's a little bit of balance there to make sure that everything works out. But it does, and we get the result that we needed. And so now we've handled all three pieces. We have the major arc close to 0, the principal major arc, and that was handled using a contour integral where we had we had this contour integral from this Mellon transform, and the important information that we needed there was this special zeta function or Dirichlet series, however you want to think about it, of the sum of the reciprocals of the set, the sum of A to the negative S. That was where our main term came from. And then the first error term was from the principal major arcs, where we needed to understand the distribution of A in residue classes. And then the minor arcs, we ended up having to analyze these special Weyl sums between where we need to know this E of A theta or A J theta, say, where A is running out through our set A. So, so those three spots are really where we needed information about the particular set A, and where it forked off, where we had to consider which restricted partition function are we actually looking at. So it seems reasonable that we could extend this method to continue to study further restricted partition functions, as long as we had all of the necessary information that we need. So we need to understand the behavior of the special zeta function. We need to understand how A behaves in residue classes, and we need to have good estimates on these Weyl sums. And so if there are other sets that we have all this information, then we can plug it into this machinery and get asymptotics for more general restricted partition functions. I will say that it's a little bit rare to have, like, this is all the information that we need, but that's not a small amount of information about the set A, right? We need to, if we understand how A is distributed in residue classes, then we need to know that it's structured in a particular way, and then having the zeta function also behave nicely is, and the Weyl, like, so it's a special kind of set that actually works for this, but there are other sets where you do have this information, or where maybe you have two pieces and you can spend some time thinking about how to combine certain things in the literature to get that third piece. I currently have a graduate student working on this for partitions into square-free numbers. And I think he's also going to look at partitions into sums of squares, which seems a little bit meta partition, but is actually an interesting set to look at.
I guess another,
So, yeah.
I guess, modern example of your is numbers.
Yeah, you could look at smooth numbers as well. Yeah.
There's a nice paper by I think a couple previous students of sound, maybe. I read from 5 years ago. I can find it, but it's
Yeah. I haven't seen that, but I believe it.
Oh yeah, no, I remember. Yeah, so I think the breakthrough was from mathcal as well. So method for smooth
Okay, great.
numbers,
Yeah.
and then they kind of use this for the stuff. I can send it to you.
Cool, thanks. Yeah, so yeah, so that's, I'm just interested in seeing if there are other sets that have this sort of same, we know all of this information about, and we can just plug into this machinery and get more restricted partition functions. And so I will stop there. I think I'm a little early, but.
Either of these work? No. All right, well, we'll just speak loudly. Well, thank you, Ayla, very much for a very interesting talk and a really beautiful conceptual summary of the circle method. Anybody that has worked in the circle method before, of course, it's a simple sounding idea, but anybody that's actually worked with it knows that it's very difficult to get the details right, and even more difficult to summarize them in such a conceptual, simple, almost a plug and play sort of way. Any questions?
So for what kind of these sets do we have an actual formula, like whether or not type series?
So the 5 that I mentioned, Tannenbaum has some work where he has like a whole class, he's using the saddle point method, but he has a whole class of sets where it works. And his class includes any polynomial value, and like it's sort of a generalization of the idea of the polynomial values. It wouldn't work for primes or prime powers though, because he's requiring that this zeta function have a continuation beyond the, like to the left half plane or whatever. Like he's requiring analytic continuation of the zeta function, which you can't do for primes and prime powers because you run into these logarithmic singularities. And so basically pretty much anything where if the zeta function has analytic continuation to the whole complex plane, then Tannenbaum's method should work, and you can get that. So that's one where everything is known. But
I guess one additional thing is not only normal for continuation, but you also need like moderate growth in vertical strips, which really sounds like a pedestrian thing, but for some of these zeta functions is actually not. Can't even write the contour integral down because it just grows too fast.
oh yeah, to make sure that
Yeah, exactly, to make sure the
Right.
integral actually makes sense. So-
yeah.
So everything is things we usually take for granted.
Yeah, I usually am just like, obviously the top goes to 0, right? But yeah, you do have to be careful.
Yeah, like I remember from this Matsumoto ranking, there was like this obscure paper and they proved meromorphic continuation, but then like we had like this awkward conditions of the polynomial because we actually needed moderate growth. We actually, yeah, it was kind of just desperately trying to get something to work. But yeah, I mean, yeah, when you write these derivative series down, it's not clear.
Yeah,
I think that's also an assumption in Tannenbaum's paper, maybe. Because the-
Yeah, it's like one of the
yeah,
axioms,
yeah, I think
right?
that's in
Yeah.
his, that's in his class.
So I know when you're trying to extract coefficients from, say, modular functions and modular functions, sometimes it's better to use more convoluted contours, like over 4 circles. What you showed in the introduction is, I'm guessing, just a circle, and you're just slowly expanding.
That's right.
Are you doing that in all of these cases? It's just the best.
Yeah. All we're doing is taking this, like, that's the circle method, right? We're taking this around a circle. And like, actually, nowadays, when you hear the circle method, people are oftentimes using the orthogonality of the exponentials. If you're looking at, say like solutions to Diophantine equations, then they're actually integrating around a circle of radius 1. You can't do that with partitions because you can't write a partition as a single equation because there's an unbounded number of variables. And so that's why you have to take a smaller circle. But yeah, we are always just looking at this circle around the origin.
It doesn't make any more sense to modify the
I don't know. I don't know that it would be helpful. I haven't ever seen that done.
Fairy circles, aren't they?
Yeah, very certain.
Fairy circles, like basically algebra method type thing, or at least that's what I see.
Yeah. I mean, I guess,
Well, that's if
right.
you-
Oh, I see where you're
this is
doing.
use- Yeah,
you-
this is useful when you have modularity, right?
Yeah.
When you have various circles, you can add cusps to other cusps. Whereas here, this is kind of throwing out the.
These aren't necessarily
Exactly,
modular,
yeah.
Yeah.
Any
Yeah,
other
I
kinds of
think
contours might
hope for
be.
something
Right.
similar for some kind of set. At least, for example, on sets where you're, you're taking sets, for example, if you're taking partitions where A just contains numbers 1 modulo 5, for example, like you take a modification of the A function, and then you have modularity, and that probably is very
Sure,
simple.
but that's a
But when-
very mild.
Well, yeah.
Right. So,
That's
but
like
when
in
you're
general, what
using,
do you know about it?
when you're using major arcs and minor arcs, then you're essentially, right? Because your major arcs are at the rational points, right? And so you're breaking your circle up into these fairy arcs. right? And so maybe you're not calling it a very circle, but like, because you're only looking at the pieces that are near rational numbers, and so you do, it might be that you really are looking at that contour, just you're not calling it that, right? So.
So I have a question. So for ordinary integer partitions in the last 10 years or so, especially, there's been an explosion of interest in other types of inequalities for partitions, like log concavity, higher order degree equations, or multiplicative additive inequalities. Do you know if any, and you might need something slightly stronger than asymptotic, but maybe like a decent asymptotic with some error term, like you wouldn't need the full strength necessarily of the Folk-Rademacher formula. I was just wondering,
Yeah.
anyone for like partitions into primes or any of these types of problems has looked at like things like that, log concavity or other types of inequalities for them?
Yeah, I don't know. I haven't heard of that. But that's interesting. I should look into that and see if someone hasn't, then maybe Amita and I should do that, because we've been going back and forth on these partitions for a while. And I will say that, and I don't think I mentioned earlier, but all of those 5 results, I stated them as asymptotic equivalents for the sake of brevity, but the actual asymptotic formula, not like a Rademacher type full formula, but an asymptotic with an error term, is given in all of these papers for like an actual thing. But then in order to do that, you have to actually understand what those constants were out front. And then you get into 2 or 3 slides for one result. So I
Yeah,
tried to keep it a little bit
yeah.
short on
Well,
that.
of course, yeah, if you just want to, if such inequalities exist, to say that they're eventually true is usually pretty easy just from an asymptotic, but if you actually want to prove it starts being true at a specific point, that can take a lot of work.
Yeah. I mean, there are also, I think in all of these, I want to say that in all, in these results, there's also like a difference equation.
Mhm.
Certainly in the powers and the primes and the prime powers. I'm not sure if Burton's RSQ, Mulligan's RSQ did some other analytics on their partitions, but like a difference equation of like Pn minus 1, so that you can see how fast that grows. And so that would help, right, with concavity.
Questions? Now let's thank Ayla again. So talks will resume at 2:30, but I believe we've been making afternoon coffee. You know,